In this lesson, we are going to look at how to predict the products of each reaction type. The file and the instruction for the reaction type flipbook are posted on Canvas. I strongly encourage students to download and create this flipbook. You do need to print it double-sided in order to assemble it correctly. What it does is allow you to sort the questions that you should be asking yourself in order to identify the reaction type for both organic and inorganic reactions. For example, if we ask the question, are the products CO2 and water, when we open that flap, we see, oh, well, that's a combustion reaction, that organic compounds combust in the presence of oxygen to produce CO2 and water. We see a sample reaction and then some other examples of that. So those questions will help you distinguish between the different types of both organic and inorganic reactions. The first step in being able to predict products of a reaction is to identify each type of reaction. For reaction number 1, see if you can identify the type of reaction. Since we have a double bond and we're adding Cl2 to form a product which has 2 Cl atoms attached, this is an addition reaction. Now let's look at number 2. For number 2, we're adding water and we are breaking the molecule apart. We know it's not an addition reaction of water because there's no carbon-carbon double bond. We cannot add across a carbon-oxygen double bond. So the only other option with water is dealing with a hydrolysis reaction. So we add water and break the molecule apart, which is consistent with the products. So we break it between the carbonyl carbon and the nitrogen, and we add an H and an OH to form a carboxylic acid and an amine. Now check out number 3. In this case, we have an alcohol, and we have all single bonds, and we're forming a water, and we produce a molecule with a double bond. This is an example of an elimination reaction. Here, we take off an OH, and remember there are also H atoms here, so we're taking off an H there and forming the double bond to get an elimination reaction. And this is hydrolysis. Now let's look at a couple of examples where we're predicting the product of the reaction. What do you think the product is for CH3CH3 plus Br2? Because we don't have a double bond, we can't have an addition reaction. So we can only add one of the Br atoms. As a result, we are going to get option C. We are doing a substitution reaction where we are replacing one of the hydrogens on the carbon with a bromine atom. What is the product of the hydration of this molecule? Because it's a hydration reaction, we need to determine first if we have to apply Markovnikov's rule. And the way we do that is to determine the number of hydrogens attached to each carbon involved in the double bond. For the carbon on the left, there are already 4 bonds, so there are no hydrogen atoms there. For the carbon on the right, there are 3 bonds, and so there's 1 hydrogen. As a result, the hydrogen is going to go where there are more hydrogen atoms, and the OH will go on the other atom. So A is the correct answer. We have an OH that attached to the carbon on the left side of the double bond, and then the H that attached to the right side. In this case, I'm showing explicitly the H that was added, but know that there's also another H that was not shown in the reactant or the product. Be aware that in some problems, it won't show the added H. Even if this just showed the H, because the other 2 hydrogens would be implied, that would still be correct. What is the product when 2-butene is hydrated? It's another hydration, so we need to look at the number of hydrogen atoms attached to each carbon involved in the double bond. They both have one hydrogen, so there is no preference as to which carbon the OH group attaches to. As a result, B is the correct answer because we see our backbone of 4 carbons, so we match that, and then we add the OH group. Now, you may be asking, why did we add it to the one on the left instead of the one on the right? Well, let's look at what we would get if we added it to the one on the right. Notice, in the original product that's drawn on the page, we see that we have an OH group attached to the second of 4 carbons. If we look at the new one I drew, where we added it to the one on the right, we see we have an OH group on the second of 4 carbons. It doesn't matter that the orientation is different. What matters is that the backbone is the same with 4 carbons, and the OH is attached in the same place on both. So these are actually the same molecule. What is the product of the condensation of ethanoic acid and methanol? Even if you don't know what these names mean, there are a few things that can give you a clue to know which molecule is which. This tells us we have eth in there, which tells us we have 2 carbons. The oic acid tells us we're dealing with the carboxylic acid, so we have to have a C double bond O, OH. Methanol, the meth tells us 1, and the OL tells us that we're dealing with an alcohol. What do you think the product is? So the first thing we have to look at is we're dealing with a condensation reaction. This means 2 things are coming together, and we're going to lose a water molecule in the process. We're not ever going to lose the oxygen involved with the carbon-oxygen double bond. This is very stable. But what we see is we have an OH group on both molecules, and so I'm actually going to remove the H from one and the OH from the other. That's going to form the water. It doesn't matter if you remove the OH from the left molecule and the H from the right, as long as you remove an H and an OH. Then what will happen is we're going to form a new bond, and that new bond will be from this oxygen over to this carbon, because there's not another carbon in here. It's carbon directly bonded to the O, which we have removed. So the oxygen bonds to this carbon. So when we look at our possibilities, when we look at A, we see that the double bond O is gone. That's where they formed the bond. So that can't be correct. When we look at B, we see that we've got our basic structure with the CH3, double bond O, and then we have OCH3. So that's the correct answer. When we look at C, the problem we have is that there are 2 oxygens, and that's not going to happen. So we're only going to have 1 oxygen atom in there.